So, welcome back. So we've talked about forward stepwise selection and backward stepwise in all subsets, as well as some techniques for choosing the model size. All of those methods fit by least squares. So whenever we consider model, a subset, we always fit the coefficients by least squares. Now we're going to talk about a different method called shrinkage, namely two techniques, ridge regression and lasso. And as we'll see that these methods do not use full least squares to fit, but rather a different criterion that has a penalty that will shrink the coefficients towards typically 0. And we'll see these methods are very powerful. In particular, they can be applied to very large data sets, like the kind that we see more often these days, where the number of variables might be in the thousands or even millions. So,
and one thing that's worth mentioning is that like ridge regression, lasso, and shrinkage methods like this are a really contemporary area of research right now. I mean, there's papers every day written by statisticians about variants of these methods and how to improve them and that sort of thing, as opposed to some of the other things that we've covered so far in this course where, you know, the ideas have been around for 30, 40 years.
Although actually ridge regression I think was invented in the 70s, but it is true that it wasn't very popular for many, many years. It's only sort of with the advent of fast computation in the last 10 years that it's become very, very popular along with the lasso. So some of these methods are old, some are new, but they're really quite hot now in their applications. So ridge regression. Well, let's first of all just remind ourselves what least squares is. The training error. So the RSS, or training error, is the sum of squares deviation between y and the predictions. So when we do least squares, we simply find the coefficients that make this as small as possible. Now, with ridge regression, we're going to do something a little bit different. We're going to use training error, RSS, but we're going to add a penalty to that, namely a tuning parameter, which we'll choose in some way, and as you can guess, it'll be by cross-validation, times the sum of the squares of the coefficients. So we're going to try to make this total quantity small, which means we're going to try to make the fit good by making the RSS small, but at the same time, we're going to have something which is going to push us the other direction. This is going to penalize coefficients which get too large, right? The more non-zero a coefficient is, the larger this is. So we're going to pay a price for being non-zero, and we'll pay a bigger price the larger the coefficients are. So it's basically fit versus the size of the coefficients. And that penalty is called a shrinkage penalty, because it's going to encourage the parameters to be shrunk towards 0. And the amount by which they're encouraged to be 0 will be determined by this tuning parameter lambda. If lambda is 0, let's go back to this. If lambda is 0, of course, we're just doing least squares, right? Because this term will be 0. But the larger lambda is, this tuning parameter, the more and more of a price we'll pay for making these coefficients non-zero. If you make lambda extremely large, then at some point the coefficients are going to be very close to 0, because they'll have to be close to 0 to make this term small enough, right? No matter how good they help to fit, we're going to pay a large price in the penalty term. So in other words, this term has the effect of shrinking the coefficients towards 0. And why 0? Well, 0 is a natural value. Remember, 0, of course, if a coefficient is 0, the feature is not appearing in the model. So if you're going to shrink towards some value, a 0 is a natural place to shrink towards. And the tuning parameter, the size of the tuning parameter, it trades off the fit versus the size of the coefficients. So as you can imagine, choosing a good value for lambda for the tuning parameter lambda is critical, and cross-validation is what we're going to use for this. So let's see what happens for the credit data. Well, let me just go back here. So if we think of this for a fixed value of lambda, we have to find the smallest value of this criterion. And again, it's just an optimization problem with actually a very simple solution. And there are computer programs for doing that. So I've used such a program, and we'll talk actually in the R session about an R function for doing ridge regression. But let's see what it looks like in this example, in the credit example. So here we've plotted the coefficients, standardized coefficients versus lambda for the credit data. And let's see what happens. Well, first of all, on the left-hand side, lambda is close to 0, so there's almost no constraint on the coefficients. So here we're pretty much getting the full least squares estimates. And now as lambda gets larger, it's pushing the coefficients towards 0, because we're paying more and more of a price for being non-zero. In the extreme over here, where lambda is a little more than, maybe more than 10,000, the coefficients are all essentially 0. In between, they're shrunken towards 0 as lambda gets larger, although not uniformly so, right? Like this, the rating variable actually gets bigger for a while and then shrinks back down to 0.
And I remember when I was a student seeing this figure again and again. Actually, it was in a class that Rob was teaching and being totally confused for like 3 lectures. Okay. So I just want to spare everyone this confusion in case anyone shares the confusion I had. So like if we look here, this red line indicates the spot at which lambda equals 100. And at that spot, the income coefficient takes on a value of like negative 100. These other 6 coefficients here are all around 0. Student takes on a value of around 100. Limit and rating take on values of around 250. And so the point is, what we're plotting here is a ton of different models for a huge grid of lambda values, and you just need to choose a value of lambda and then look at that vertical cross-section.
Good. And as Daniela said, if we chose the value of lambda about, was that 100, then it seems like it chooses about 3 non-zero coefficients, the black, the blue, and the red, maybe 4. And then these guys here are basically essentially 0, the gray ones.
So they're not quite 0, but they're small.
Yeah. Right, exactly. So an equivalent picture on the right now, we've plotted the standardized coefficients as a function of the L2 norm, the sums of the squares, the square root of the sum of the squares of the coefficients divided by the L2 norm of the full least squares coefficients.
So Rob, what's the L2 norm?
Okay. The L2 norm, so the L2 norm of the vector beta 1 through beta p, it's written this way. So the L2 norm, so it's the square root of the sum of beta j squared. All right, so this is that's the L2 norm, and so that's it. So we see here when the L2 norm is 0, so when the coefficients are all 0, the L2 norm is 0. That corresponds to the right side of this picture. So the lambda is very large here. It's large enough that it's driven the L2 norm down almost to 0. So the coefficients are basically 0. And then on the right, lambda is very small, and we get the full least squares estimates. And in between, we get, again, a shrunken coefficient. So these two pictures are really the same, but they've been flipped from left to right.
And the x-axes are parameterized in a different way.
Right.
So Rob, why does this x-axis on the right-hand side go from 0 to 1? Why does it end at 1?
Oh, because we plotted it ends at 1 because we're plotting as a function of this standardized L2 norm. So at the right-hand side, we have basically the full least squares estimates, so these numerator and denominator are the same.
Right, so on the right-hand side here, on this right-hand plot, lambda is 0. Right. And so your ridge regression estimate is the same as your least squares estimate, and so that ratio is just 1.
Exactly. Okay. I think we've actually just said all this. Thanks to the questions from Daniela. Right, so there's the L2 norm defined. I wrote it in the previous slide, and that's what was used for the plotting axis. One important point with ridge regression is that it matters whether you scale the variables or not. Now, just to remind you, if you just do standard least squares, so standard least squares is what's called scale invariant. If I multiply a feature by a constant, it's not going to matter because I can divide the coefficient by the same constant and I get the same answer. So in least squares, the scaling of the variable doesn't matter. So whether I measure a length in feet or inches is not going to matter because the coefficient can just account for the change in units. But it's a little bit subtle here now. For ridge regression and penalized methods like ridge regression, the scaling does matter in an important way. And that's because if we go back to the definition of ridge regression, right, these coefficients are all put in a penalty together, and there's a sum of squares. So if I change the units of one variable, it's going to change the scale of the coefficients. Well, if I change the units of one variable, the coefficient has to change to try to accommodate for that change. But it's competing against the coefficients for other features. So because they're all put together in a penalty in a sum, the scale of the features matters. And as a result, it's important to standardize the predictors in regression before applying ridge regression. So in most cases, before you do a ridge regression, you want to standardize the variables. What does that mean to standardize the variables? Well, you take the variable or feature and you divide it by the standard deviation of that feature over all the observations. And now the standard deviation of this guy is 1. And you do that for each feature, and that makes the features comparable and makes their coefficients comparable. So let's see an example of ridge regression compared to least squares. Here's a simulated example with 50 observations and 45 predictors, in which all of the predictors have been given non-zero coefficients. So we see on the left, we see the bias in black, the variance in green, and the test error in purple for ridge regression as a function of lambda, and the same thing on the right as a function now of the standardized coefficients of the two norm of ridge regression divided by the two norm of full least squares. So again, these are the same pictures essentially, but the x-axis have been changed. But let's look over here. We can see that what happens, well, the bias as we move, so full least squares is over here on the left, right? Lambda is close to 0. As we make lambda larger, the bias is pretty much unchanged, but the variance drops. So ridge regression, by shrinking the coefficient towards 0, controls the variance. It doesn't allow the coefficient to be too big, and it gets rewarded because the mean square error, which is the sum of these two, goes down. So here's the place where the mean square error is minimized, and it's lower than that than the full least squares estimate. So in this example, ridge regression has improved the error, the mean square error of full least squares by shrinking the coefficients by a certain amount. And we see the same thing in this picture.
And actually, this U-shaped curve that we see for the mean squared error in this figure in purple comes up again and again, where when we're considering a bunch of different models that sort of have different levels of flexibility or complexity, there's usually some sweet spot in the middle that has the smallest test error, and that's really what we're going for. So that's what's marked as an X in these two figures.
So I want to go back to this picture of ridge. Let me clear the... And one thing you might have noticed here that we mentioned is that the coefficients are never exactly 0. They're close to 0, like here. These gray guys are all close to 0, but they're never exactly 0. Matter of fact, you can show mathematically that unless you're extremely lucky, you're not going to get a coefficient exactly of 0. So ridge regression shrinks things in a continuous way towards 0, but doesn't actually select variables by setting a coefficient equal to 0 exactly.
But it seems like a pity in this example, right? Because all those gray variables are so tiny, it would just be more convenient if they were 0, right?
Which is a great setup for the next method, called the lasso.